Have you ever contemplated the immense power harnessed within the heart of an atom? Picture this: an entity so minuscule it's virtually invisible to the naked eye, yet within it lies a force so potent it can fuel our cities, power our industries, and in moments of great folly, even level them to the ground. This is the paradox of nuclear reactions. Nuclear reactions, the atomic dances that occur in the heart of an atom, can be broadly classified into two types: nuclear fission and nuclear fusion. Nuclear fission is akin to splitting the proverbial apple. It involves dividing a heavy nucleus, like uranium or plutonium, into two or more lighter nuclei. This division releases a tremendous amount of energy, and it is this energy that we have harnessed in nuclear power plants, and regrettably, in nuclear weapons. On the other hand, nuclear fusion is the mirror image of fission. It's the process of merging two light nuclei, often hydrogen isotopes, into a heavier nucleus. This fusion, the very process that powers stars like our sun, releases even greater amounts of energy than fission. And unlike its counterpart, fusion doesn't produce long-lived radioactive waste, making it a more attractive, albeit challenging, prospect for energy production. These nuclear reactions, fission and fusion, represent the duality of mankind's relationship with atomic power. On one hand, they've given us the means to meet our ever-growing energy needs, independent of fossil fuels. On the other, they've presented us with some of our greatest challenges, from managing radioactive waste to preventing the proliferation of nuclear weapons. But beyond these challenges and opportunities, nuclear reactions embody a deeper truth about our universe. They reveal how the cosmos, in its infinite wisdom, has stored immense power in the most unlikely of places, the heart of an atom. It's a reminder of the untapped potential that lies within seemingly insignificant entities, a potential that we, as a species, have only begun to comprehend and harness. So begins our journey into the heart of the atom, a journey of unimaginable power and potential. Before we move on, here's a reminder to like this video and subscribe to SciSips. At the heart of an atom, a delicate balance of forces reigns supreme. This equilibrium is the stage for the atomic ballet of nuclear fission, a process that splits a heavy nucleus into two or more lighter ones, liberating a significant amount of energy. Imagine a hefty dancer like uranium or plutonium, spinning and twirling until it splits into two lighter dancers, all while emitting an energetic encore of neutrons and gamma rays. To appreciate this performance, we must first understand its choreography, which begins with binding energy. This is the glue that holds the protons and neutrons in the nucleus together. The higher the binding energy, the more stable the nucleus. However, in large nuclei like uranium, the outermost protons are less tightly bound, making them more susceptible to a splitting move called fission. But what prompts this atomic pirouette? Here's where criticality comes in. If a slow-moving neutron strikes a fissile nucleus, it can cause the nucleus to become unstable and split. This releases more neutrons, which can then trigger a chain reaction if they, in turn, collide with other fissile nuclei. This self-sustained sequence of fissions is what we call a critical chain reaction, the fundamental principle behind nuclear reactors and atomic bombs. But with every dance, there's a fallout. In the nuclear world, this fallout refers to the radioactive particles that are released during fission. These particles can cause damage to living tissue and the environment, marking a darker side to the fission process. Despite these challenges, nuclear fission has its advantages. For starters, it's a mature technology. We've been harnessing the power of fission for over 70 years, ever since it lit up the first atomic bomb and powered the first nuclear reactor. Fission also boasts a high energy density. The energy released by the fission of just 1 gram of uranium, 235, is equivalent to the combustion of thousands of tons of coal. This makes fission a powerful ally in our quest for energy independence from fossil fuels. However, this power comes with its own set of problems. The fission process produces radioactive waste that remains hazardous for thousands of years. Managing and disposing of this waste safely is a significant challenge. Then there's the risk of nuclear accidents, as we've seen in Chernobyl and Fukushima. These disasters remind us of the catastrophic consequences when control over the fission process is lost. Finally, there's the issue of weapons proliferation. The same process that powers our cities can also fuel the most destructive weapons ever made. Keeping nuclear technology out of the wrong hands is a constant concern. Fission, although powerful, is not without its challenges and risks. As we delve deeper into the atomic world, we must navigate these complexities with care, balancing the immense power of fission with our responsibility to use it safely and ethically. As we'll see in the next scene, there's another player in this atomic dance, nuclear fusion, which offers its own set of promises and challenges. Imagine harnessing the power of the stars. This is the promise of nuclear fusion. Nuclear fusion is the process that fuels the sun and other stars. Its magic lies in the merging of two light nuclei, typically hydrogen isotopes, into a heavier nucleus. In this process, a considerable amount of energy is released, even more than what nuclear fission can yield. At the heart of nuclear fusion is plasma, a state of matter that's neither solid, liquid, nor gas. It's a soup of charged particles, where electrons are separated from their nuclei. In the sun, the immense gravitational pressure creates the right conditions for fusion to occur. However, here on Earth, we need to recreate those conditions within a device, and that's where the challenge begins. The fuel for fusion comes from deuterium and tritium, two isotopes of hydrogen. Deuterium is plentiful, found in seawater, while tritium is rare but can be produced in a reactor from lithium. The goal is to heat these isotopes to such an extreme temperature that they form a plasma and collide with enough force to overcome their natural repulsion, causing them to fuse and release energy. But how much energy? Well, that's where the concept of energy break-even comes into play. Energy break-even is the point where the energy produced by the fusion reaction equals the energy put into it. So far, we've managed to achieve this in experimental settings, but the challenge is to sustain it in a practical, power-generating scenario. The allure of fusion is undeniable. It's a clean energy source, producing no long-lived radioactive waste. Its fuel is abundant, with deuterium in seawater and tritium producible from lithium. And unlike fission, it poses no risk of weapons proliferation, as the process is too complex and requires too precise conditions to be weaponized. However, the path to harnessing fusion is strewn with hurdles. The technology needed to sustain a fusion reaction is complex and still under development. The supply of tritium, a key component for fusion, is limited, and producing it in adequate quantities is a challenge. And there's the question of commercial viability. As of now, the costs associated with fusion technology are high, and it remains to be seen if fusion energy can be produced at a price that's competitive with other energy sources. Fusion, a process of immense potential, remains elusive in the face of significant challenges. But, with continued research and technological advancements, the promise of harnessing the power of the stars may one day become a reality. For in the heart of the atom lies not just immense power, but also the potential to reshape the course of human civilization. Fission or fusion, a conundrum of atomic proportions. As we delve deeper into the atomic world, we find ourselves at a crossroads. On one hand, we have nuclear fission, a mature technology that's been with us since the mid-20th century. One that's proven its high energy density and independence from fossil fuels. Yet it's a path laden with risks. Radioactive waste, the potential for nuclear accidents, and the ever-looming issue of weapons proliferation. On the other hand, we find nuclear fusion, the process that lights up our sun and every star in the cosmos. Fusion involves merging two light nuclei, typically isotopes of hydrogen, into a heavier nucleus, releasing an even greater amount of energy than fission. Unlike its counterpart, fusion does not produce long-lived radioactive waste, making it a cleaner alternative. It offers abundant fuel and sidesteps the problem of weapons proliferation. However, it's not without its own set of hurdles. The technology is still in its infancy, and significant scientific and commercial challenges need to be overcome before it becomes a viable energy source on Earth. The road to harnessing fusion energy is fraught with complexities. It involves achieving a state of plasma, a hot, electrically charged gas, and sustaining it under conditions of extreme temperature and pressure. The most promising fusion reaction involves deuterium and tritium, two isotopes of hydrogen, but the supply of tritium is limited, and its handling requires utmost care due to its radioactivity. Then there's the challenge of energy break-even, where the energy produced by the fusion reaction equals or surpasses the energy put into initiating the reaction. These complexities make choosing between fission and fusion a monumental task, one that requires not just scientific acumen, but also ethical responsibility. As we weigh the advantages and disadvantages of both, we must consider the long-term impacts on our planet and future generations. Fission, while reliable and mature, grapples with waste management and proliferation concerns. Fusion, though holding immense promise of clean, abundant energy, battles technological hurdles. Both technologies stand on a precipice, their futures intertwined with our own. A possible future sees continued advancements in reactor design and waste management, making fission safer and more sustainable. Concurrently, groundbreaking research could push the boundaries of fusion technology, leading to breakthrough advancements and eventual commercialization. Ultimately, the future of nuclear power may lie in a diversified portfolio, where both fission and fusion contribute to a cleaner, more secure energy future. The choice between fission and fusion is not a simple one, each holding its own set of risks and rewards. As we navigate these complexities, we must remember that we're not just dealing with immense power, but also the potential to reshape the course of human civilization. The atomic world is a labyrinth of opportunities and challenges, and the path we choose will determine our destiny. The future of nuclear power, shrouded in uncertainty, holds immense promise. As we look ahead, the potential for advancements in nuclear technology is vast. The journey of both fission and fusion towards widespread adoption is fraught with challenges, but their promise is too great to ignore. Fission, despite being a mature technology, is not without its problems. The generation of high-level radioactive waste is a pressing issue, necessitating the development of improved waste management strategies. This includes the design of advanced reactors capable of reducing the long-term radioactivity of waste, and the investigation into deep geological repositories for the safe, long-term storage of spent fuel. The threat of nuclear accidents also looms large, driving the push for safer reactor designs. The advent of Generation 4 reactors, with their inherent safety features and improved efficiency, could mark a significant step forward. These designs aim to minimize the risk of core meltdowns and reduce the potential for weapons proliferation, addressing two of the most significant concerns associated with fission. Simultaneously, the quest for fusion power continues. Fusion, the process that powers our sun, offers the promise of abundant, clean energy without the long-lived radioactive waste associated with fission. Yet, the road to commercial fusion power is fraught with technological hurdles. The creation and containment of the high-temperature plasma necessary for fusion reactions presents significant challenges. The development of materials capable of withstanding these extreme conditions and the design of magnetic confinement systems to contain the plasma are areas of active research. Similarly, the supply of tritium, one of the fuels for fusion reactions, is a concern. While tritium can be bred in a fusion reactor from lithium, this process is not yet commercially viable. The development of efficient tritium breeding technologies is therefore a critical aspect of the path to commercial fusion power. Despite these challenges, the potential rewards of fusion power are immense. The successful commercialization of fusion technology could revolutionize our energy landscape, providing a virtually limitless source of clean, safe energy. As we move forward, it's likely that the future of nuclear power will not hinge on a single technology. Instead, we may see a diversified portfolio, where both fission and fusion play key roles. Advanced fission reactors, providing reliable, high-density energy, could work in tandem with fusion power plants, offering an abundant, clean energy source. This diversified approach could help to mitigate the risks associated with each technology, while maximizing their respective benefits. It could enable a more flexible, resilient energy system, capable of meeting our growing energy needs, without compromising the health of our planet. The journey to this future will not be easy. It will require substantial investment, innovative research, and the courage to overcome significant technical and regulatory hurdles. But the rewards could be profound. The choice between these two giants of the atomic world is not a simple one. Each path presents its own set of risks and rewards. The future of nuclear power, therefore, lies not solely in the hands of scientists and engineers, but also in those of policymakers and the public. Decisions made today will shape the course of nuclear power for decades to come. These decisions must be informed by rigorous scientific understanding, ethical considerations, and a commitment to the long-term sustainability of our planet. In the heart of the atom lies not just immense power, but also the potential to reshape the course of human civilization. Don't forget to subscribe to SciSips on YouTube.